Okay, next we have the second oral presentation. The title is Uncertainty-Supervised Interpretable and Robust Evidential Segmentation. The presenter is An Sui from Fudan University.
Thanks. Good morning, everyone. I'm Sui An from Fudan University. It's a great pleasure to present our work titled Uncertainty-Supervised Interpretable and Robust Evidential Segmentation. I'll guide you through the main ideas and contributions of this work. While traditional black box models achieve high accuracy, they often assign high probabilities to miss predictions. This overconfidence is dangerous in high-stakes domains like healthcare. Thus, accuracy alone is insufficient. We need reliability and trustworthiness. Confucius once said, "To know is to know. Not to know is not to know." That is true wisdom. Therefore, for a West model, it's crucial to express "I don't know," which is the core of the concept of uncertainty. Methods like evidential learning have been proposed to quantify this uncertainty, claiming to enhance reliability and safety. However, existing methods quantify this uncertainty merely as scalar values without identifying their underlying sources as humans typically would. Consequently, these values remain inherently unexplainable. In other words, uncertainty should tell us why, not just how much. Building upon Confucius' wisdom, we propose a greater form of intelligence, not only to know what I don't know, but also why I don't know. To this end, we introduce uncertainty supervision, which uses human intuition to guide estimation. As a result, the model not only tells us "I don't know," but also explains why I don't know. For example, visually ambiguous regions naturally demand a higher uncertainty for its prediction. So, if we can encode these logistics into the model, the uncertainty estimation will be more interpretable. This shifts uncertainty from passive estimation to active supervision. To achieve this, we introduce three guiding principles of uncertainty supervision. For principle one, we measure the ambiguity using the gradient at each image pixel around the boundaries between different classes. As shown in the figure, clear boundaries with higher gradients in yellow box lead to lower uncertainty, while ambiguous boundaries with lower gradients in red box lead to higher uncertainty. To enforce this, we design a gradient-based supervision loss. As shown in the equation, we penalize cases where the uncertainty increases with the gradient. For principle two, we perturb the original image with small noisy patches. Patches close to the boundaries are more sensitive to noise. When the noise amplitude is stronger, the uncertainty should increase, and vice versa. To enforce this, we design a noise-based supervision loss. It penalizes cases where the uncertainty doesn't follow the expected trend, thereby enhancing nearby interpretability. For principle three, we assume that pixels sufficiently far from boundaries should have near zero uncertainty, regardless of noise. The figure shows that patches far from boundaries are insensitive to noise, without any highlights in their uncertainty maps. Combining this remote loss for robustness and the nearby loss for interpretability, mentioned before in principle two, creates our noise-based supervision loss. Finally, the overall loss function combines the standard evidential learning loss and the weighted sum of both our gradient-based and noise-based supervision losses. Beyond the traditional metrics, we further propose two new metrics to evaluate whether the predicted uncertainty is aligned with the human intuition: uncertainty correlation coefficient, UCC, and uncertainty ratio, UR. For example, UCCG evaluates the gradient-related principle by calculating the coefficient between the gradient and uncertainty across pixels near boundaries, well, URG calculates the ratio of pixel pairs whose gradient and uncertainty differences have the correct sign. Similarly, the noise-related principle can be evaluated accordingly. So by checking whether the correlation coefficient between gradient or noise and uncertainty, as well as ratio, satisfy the aforementioned principles, we can quantify the interpretability of the uncertainty. We conducted an ablation study to confirm the contributions of the proposed noise-based supervision loss, gradient supervision loss, and the hard sample detection strategy. Our method in the first row achieves the best UCC and UR while delivering a comparable DICE and a 95% D. And you should note that only with both our gradient-based and noise-based supervision losses do we get correct UCC signs. Negative for gradients, positive for noise amplitudes. Next, we compare our approach with other methods. We achieve the best DICE and comparable 95% D. Moreover, our uncertainty consistently yield a correct sign of UCC across all datasets, while competitors might fail on at least one dataset, which indicates that our uncertainty is more aligned with human intuition. This figure illustrates the superior interpretability of the proposed method. In the first row, we show the original images and the corresponding predicted segmentation masks. In the second row, we overlay the gradients on the uncertainty difference map, as the arrow indicates that our uncertainty is more aligned with human intuition, that is, lower gradients lead to higher uncertainty, and vice versa. In the third row, we add small noisy patches to the image, and the difference maps of ours highlights only boundary locations, satisfying the principle while competitors might fail. In the final row, we apply a global noise to the entire image, and once again, only our method lights up the edges. Furthermore, we validate the robustness of our model. And as you can see, we achieve the smallest variation under different noise corruption, demonstrating highly robust to noise. To recap, our contributions are threefold. We introduce uncertainty supervision, which uses human intuition to guide estimation. We introduce two new metrics for explainable uncertainty. And we demonstrate the effectiveness and robustness with experiments. Nevertheless, this work has limitation. The supervision of the uncertainty currently is relied solely on simple yet effective ranking losses, and still awaits for a more in-depth theoretical derivation and broader extensions. Looking ahead, our method opens possibilities for more principle and theory-driven uncertainty modeling. In a nutshell, supervision does matter in uncertainty estimation. Thanks for your attention. I'd be happy to take any questions.